Good morning, everyone. This is G. Vishnumurthy, lecturer in physics, Government Degree College for Women, Wanaparthy. Today, my topic is waves and oscillations. In waves and oscillations, my topic is simple harmonic motion. In this study, we will discussing in this topic we will discussing about the definition of simple harmonic motion, characteristics of simple harmonic motion, an example for the simple harmonic motion, and simple pendulum. We know that the definition of the wave is the disturbance in a medium is known as the wave. Simple harmonic motion is also a wave, but it has some specular characteristics are there. And here you see the definition of the simple harmonic motion is such a motion in which the acceleration is directly proportional to the displacement and is directed towards the main position is called as simply harmonic motion, simple harmonic motion, and that is denoted with SHM. And know that motion in which the acceleration is always directly proportional to the displacement. When the displacement is increases, then the acceleration will be increases. When the displacement will be decreases, then acceleration will be decreases. And also it is quite opposite to the direction of the position of direction of the mean position. And here the condition for simple harmonic motion, the motion which is quite different from other motions from this three conditions. The system should have the restoring forces, the system should have inertia, the system should be frictionless. If friction is there, then the motion is called as a normal motion, and it is not called as the SHM. So when these criteria are exhibit in a motion, then the motion is called as the simple harmonic motion. And now Hooke's law. From Hooke's law, we will discussing about the simple harmonic motion. The force that is applied to a spring is directly proportional to the displacement. Is already we will discuss in previous classes. The force always is directly proportional to the displacement. So when the force is higher, then the displacement will be higher. And in the spring, in unstretched, there is no net force on the mass, or the system is in equilibrium. If the mass is displaced from equilibrium, the spring will exert a restoring force, which is a force that tends to restore it to the equilibrium position, is called as the restoring force. So from Hooke's law, we will taking as equation as F is directly proportional to x and F is equals to k into x, where k is called as the spring constant, F is called as the elastic force, and x is called as the displacement. An expression for the acceleration of the body executing simple harmonic motion. So consider a mass m attached to one end of the elastic spring. Here the m, elastic spring which can move freely on a frictionless horizontal surfaces. When the mass is released, it begins to vibrate about its mean or equilibrium position. But due to elasticity, spring opposes the applied force which produces the displacement. This opposing force is called as the restoring force. From this figure, we will see the mean position is there. So m is fixed at the end of the spring. Then we will apply some external force from this side. Then that's why the spring will be stretched. And after stretching after stretching, we will release the spring. Then it will be vibrate from vibrate within the mean position. So that force is called as the restoring force. If there is no restoring force act on the spring, then the spring could not comes in mean position. So when the mass is released, it begins to vibrate about the mean or equilibrium position. But due to the elasticity, spring opposes the applied force which produces the displacement. This opposing force is called as the restoring force. So we got the expression for the acceleration of the body executing the simple harmonic motion. So the restoring force is written by Fr is equals to minus k into x. Here why we are taking as minus on the equation, the minus is indicate the restoring force is always acting opposite side of the displacement or opposing the displacement. That's why we will put a negative value in front of the k, and k is called as the spring constant, x is called as the displacement of the spring, and Fr is called as the restoring force. So if small a is the acceleration produced by force capital F in mass spring system at any instant, then according to Newton's law of motion, we know that the Newton's second law of motion, that is F is equals to ma, but here is m is called as the acceleration, and acceleration is denoted with the dx by dt or x double dot. Here x double dot is called as the double differentiation of displacement. So therefore F is equals to m into x double dot. Here x double dot is equal to dx by dt or d square x by dt square. Now we are substituting that equation, then mx double dot is equals to minus kx is equals to x double dot is equal to minus k by m into x. So therefore k by m is equals to constant, that's why we will put k by x is equals to constant, then a is directly proportional to minus x. So therefore from above equation we can write as x double dot plus k by m into x is equals to 0. Then x is equals to a cos of omega t plus pi, and omega is equals to root of k by m. Then this value and this value substituting in this equation, we get as and also velocity can found differentiating the displacement. Here you see from x is equals to a cos of omega t plus pi, and omega is equals to root of k by m, and also here you substituting k by m is equals to omega or k by m is equals to omega square, then the equation is equals to d square x by dt square plus omega square dx by omega into x is equals to omega into x is equals to 0. Then this equation is called as the simple harmonic equation. Here you see x double dot is equals to d square x by dt square, and k by m is equals to, from this equation we have omega square, and x is equals to, so therefore d square x by dt square plus omega square x is equals to 0, where omega square is equals to k by m. This equation indicates the simple harmonic motion or the motion of the simple harmonic oscillator. Now we are going to velocity can be found differentiating the displacement. We know that the displacement x is equals to written as x is equals to a cos of omega t plus pi. Then from this equation we will get the velocity of simple harmonic motion. So here then we will differentiate this equation, that is dx by dt with respect to t. So therefore dx by dt, and the rate of change of displacement is known as the velocity, that's why we will taking as the velocity v. So therefore here a cos of omega t plus pi, if you differentiating this equation, then we got as minus a omega sin of omega t plus pi. So from this equation we getting another definition, that is acceleration. Acceleration can found by differentiating above equation, that is velocity equation. So therefore v is equals to dx by dt, again it will be differentiating with respect to t, then d square x by dt square. We know that d square x by dt square is equals to acceleration a, so therefore a is equals to A. Here we differentiating this equation with respect to t, then therefore we got as minus A omega square cos of omega t plus pi. So therefore simplifying the acceleration in terms of displacement, then we got as A is equals to d square x by dt square, and that is equals to minus omega square x. So acceleration can be expressed as A of t is equals to 2 of 2 pi f whole square of x of t. Here x is called as the displacement with respect to t and f is equals to frequency. So this equation also indicates the acceleration, and also this equation also indicates the acceleration. So this is about the velocity, acceleration and the displacement of the simple harmonic motion. Okay, now the characteristics of mass spring system executing simple harmonic motion are the characteristics of simple harmonic motion. So when a body is vibrating, its displacement from the mean position changes with time. So the value of its distance from the mean position at any time is known as its instantaneous displacement. We know that when a body is vibrating, its displacement from the mean position changes with the time, because of always the mass will be vibrating from this side to this side, this side to this side, this side to this side. So therefore every second the position and the displacement of the oscillator will be changes. So therefore that displacement is called as the instantaneous displacement. So the maximum value of displacement is known as its amplitude. We know that the maximum displacement is always called as the amplitude, that is equals to A is equals to y maximum. A is equals to y maximum or A is equals to x maximum. So a vibration means one complete round trip of the body. For example, this is the mean position, then it starts from the mean position or resting position, it goes to this side, again it will come to restoring center point, that is resting position, and then it will come to opposite side. So the displacement should be same in both sides. So if it goes to this point and then this point, then the displacement is called as the one complete rotation. So the time required to complete one vibration is called as the time period. So the time period is denoted with the capital T, and capital T is equals to 2 pi root of m by k. Here m is called as the mass of the oscillator or mass of the particle which is execute the simple harmonic motion, and k is called as the spring constant. So therefore the time taken for the one oscillation is known as the time period of simple harmonic oscillator. So it is indicated with capital T, and capital T is equals to 2 pi root of m by k. The units of the time period is equals to seconds. And now the number of cycles per second. A cycle is a complete round trip is called as the frequency. We know that the number of oscillations per second is called as the frequency. At the same time, the number of oscillations per second is called as the frequency, and it is denoted with the f, and f is equals to 1 by t. Then we will substitute the time period. T is equals to 2 pi root m by k. Then we got as f is equals to 2 pi root k by m. So if t is time period of a body executing simple harmonic motion, its angular frequency can be written as this equation. So omega is equals to 2 pi by t. Then we will substitute t is equals to 1 by f. Then we got as omega is equals to 2 pi f. So these are the characteristics, that is the time period and the frequency and angular frequency of the simple harmonic oscillator. Now the phase angle. The angle theta is equals to omega t, which specifies the displacement as well as the direction of the point executing the simple harmonic motion, is known as the phase angle. And the phase angle is denoted with the theta, and theta is equals to omega t. And now the general equation for the how we will got as, that is x of t is equals to a cos of 2 pi f t plus pi, whereas x is equals to displacement capital A is equals to amplitude of the acceleration as oscillation, and F is equals to frequency, and T is equals to time period, and pi is equals to pace of oscillation. So if there is no displacement at time t is equal to 0, then the pace is pi is equals to pi by t. Okay. Now it is showing, this is showing with the graphical representation like this. Here the graphical explanation about the displacement, velocity and the acceleration in between the 0 to t by 4. At t the displacement is equal to 0, but at t the velocity is negative, but at the t is equals to, at the time period t is equals to, the acceleration must be 0. Okay, so these are the graphical explanation about the displacement, velocity and acceleration. Now the example for the simple harmonic motion is loudspeaker. The cone of a loudspeaker, that is the center point of loudspeaker is called as the cone shape. The oscillations, loudspeaker oscillates in simple harmonic motion at a frequency of 262 Hz. So in loudspeaker, the cone shape in center is vibrating for a second, vibrations 262 vibrations per second. That's why the frequency of speaker is called as the 262 Hz. So that the amplitude at the center of the cone is A is equals to 1.5 into 10 to the power of minus 4 meter, and at t is equal to 0, then x is equals to A of small a. So what equations describes the motion of the center of the cone? And now we are going to solution. For this solution, this is the example for the simple harmonic motion, and now we will calculate the from this equation. So that is x of t is equal to a cos of 2 pi f of t plus pi. So from this equation we will calculate x of t is equals to 1.5 into 10 to the power of 4 meters, and cos of 150 t, and then countable as velocity, acceleration, so on so are calculated. Now the energy conservation in simple harmonic motion. So if the friction effect are neglected, the total mechanical energy of vibrating mass spring system remains constant. So the velocity and position of the vibrating body are continually changing. The kinetic and potential energy also change, but their sum must have the same values at any instant time. So from Hooke's law we will prove that Hooke's law is equals to F is equals to minus kx, then W is equals to integral f dx, and U is equals to minus W, and U is equals to minus of integral f dx. So U is equals to minus of integral minus kx dx, then minus of minus is equals to plus, and k integral x dx, and k into x square by 2. And now we will putting the value of displacement, that is u of t is equals to 1 by 2 k xm cos of omega t plus pi whole square. Then we will squaring the equation, then we got as 1 by 2 k x square m cos square of omega t plus pi. The kinetic energy is given as, we know that the kinetic energy is equals to 1 by 2 mv square. The kinetic energy is maximum if x is equals to 0, when the mass is at equilibrium position of k of t is equals to 1 by 2 m of minus omega xm sin of omega t plus pi whole square. Now k is equals to m omega square, therefore k of t is equals to 1 by 2 k x square m sin square of omega t plus pi. So therefore the total energy is partially, that is the potential energy and partially kinetic energy. Therefore E is equals to potential energy plus kinetic energy, that is equals to E is equals to 1 by 2 kx square. So that is equals to a constant value. Now we are going to example of simple harmonic motion is called as the simple pendulum. Now the definition of the simple pendulum: a simple pendulum is an idealized model consists of a point mass suspended by an extensible string of a length oblique fixed. When pulled to one side of its equilibrium position A to the position B through a small angle theta and release it, and it started oscillation 2 and fro over the small. So this type of body is called as the simple pendulum. Now the simple pendulum performs simple harmonic motion. Condition for simple harmonic motion is that the restoring force F should be directly proportional to the displacement oppositely directed. The path of the bob is not straight line but the arc of the circle of the radius. Now let capital T is the tension in the spring when the particle is at point B to force are acting on it. So mg the weight of the point bob acting vertically downward. Capital T the tension along the string. The weight mg can be resolved into rectangular components. Component of weight mg along the spring is equals to mg cos theta, and component of weight mg perpendicular to the string, that is denoted with the mg sin theta. Now since there is no motion of bob along the string, so that the component mg cos theta must be equal to tension in the straight T. So therefore capital T is equals to mg cos theta. Now component mg sin theta is responsible for the motion of the bob toward the mean position. Thus the restoring force capital F is indicated as F is equals to minus mg sin theta. But we know that sin theta is equals to x by L. So therefore we will putting x by L is equals to sin theta. So therefore we get as restoring force F is equals to minus mg into x by L. By second law of motion we know that F is equals to ma, that is Newton's second law of motion. Comparing those equations, then we got as ma is equals to minus mg x by L. So a is equals to minus gx by L, and we know that a is equals to minus of constant into x. Therefore a is directly proportional to minus x. So that is called as the acceleration. Now we are going to expression for the time period. We know that a is equals to minus x omega square. So therefore we substituting as a is equals to minus of gx by L. Here minus are cancelled. Then we got as a is equals to minus gx by L, and omega is equals to g by L. So therefore t is equals to 2 pi by omega. Then t is equals to 2 pi root of L by g. So this equation is called as the time period of the simple pendulum. Now we are going to frequency, that is F is equals to 1 by t, and then we will substituting time period t is equals to 2 pi root of L by g. Then we got the equation of frequency, that is F is equals to 1 by 2 pi into root of g by L. So another example for the simple harmonic motion is uniform circular motion is there. So in an object in simple harmonic motion has the same motion as of an object in uniform circular motion. Now consider the particle in uniform circular motion with the radius capital A and angle pi. Therefore we have write as displacement x is equals to a cos of pi. The particle's angular velocity in radians per second is written as d psi of dt is equals to omega. So this is the rate at which the angle pi is increasing. If the particle starts from pi of 0 is equal to 0, at t small t is equal to 0, its angle at an alternate or later time small t is simply as psi is equals to r omega is equals to omega t. So therefore as psi increases, the particles that x component is x of t is equals to a cos of omega t. So therefore that the particle in started at pi of 0 is equal to 0 in figure shows a more general solution, the situation in which the initial angle pi of 0 can have any value. Okay, this is the these are the example for the simple harmonic motion. And now we are going to damped harmonic motion. So damped harmonic motion is another motion in the waves. So the definition of the damped harmonic motion is there. In reality, there is always a resistance in any system. We neglected this when we are dealing with the simple harmonic motion. That is idealistic cases. In simple harmonic motion, we will reduce or we will neglect the resistance that is opposing the vibrations is neglecting. But actually every system will oppose the motion of itself. So that is called as the that is called as the opposing force. And now the oscillations in which the amplitude decreases gradually with time are called as the damped oscillations. So the oscillation in which the amplitude decreases gradually with the time are called as the damped oscillations. Now here we got an equation from the equation of motion for a mass m vibrating on the end of a spring of a force constant k in the absence of any damping is mx double dot is equals to minus kx. Now damping force is given by, so the equation of motion of a mass m vibrating on the end of a spring of a force constant k in the absence of any damping is denoted with mx double dot. Here the x double dot is equals to d square x by dt square is equals to minus kx. Now the damping force is given by fd, that is damping, is equals to minus c into nu, c into v, and we know that v is equals to dx by dt. So therefore minus c into dx by dt, and that is equals to minus c into x dot. Applying the Newton's second law, the total force F total on the body is F total is equals to ma is equals to m into d square x by dt square is equals to mx double dot. So therefore F total is equals to F frictional force plus F damping force. Therefore mx double dot is equals to minus kx plus minus cx dot. So from that we got as x double dot plus c by m into x dot plus k by m into x is equals to 0. Now we are putting w is equals to or omega is equals to k by m and beta is equals to c by m. Then we got an equation that is x double dot plus beta x dot plus omega square x is equals to 0, or d square x by dt square plus beta dx by dt plus omega square x is equals to 0. That equation is called as the damping general equation for the damping harmonic oscillator or damping harmonic motion. So the auxiliary equation of a differential equation, that is m square plus beta m plus omega square is equal to 0. The roots are corresponding the equation are denoted with m is equals to plus minus beta plus or minus root of beta square minus 4 omega square. So therefore m is equals to minus beta by 2 plus or minus root of beta square by 4 minus omega square. And now there are three cases are there for this case. And now the first case is that is beta square by 4 minus omega square less than 0. The system oscillates about the equilibrium position with the decreasing amplitude over a period time. So this is shown of this case, that is beta square by 4 minus omega square less than is equal to 0. Then the system oscillates about the equilibrium position with the decreasing amplitude over a period of time. So if the period of time is increasing, then the amplitude will be decreases like this. And now the second case, for example, air resistance on a pendulum or air resistance lower the amplitude of a pendulum. This is an example of light damping. And case 1 is written as beta square by 4 minus omega square less than is equal to 0. Then we get as beta square by 4 minus omega square is equal to minus n square. M is equal to minus beta by 2 plus or minus log n, and x is equals to e power of minus beta t by 2 a sin of nt plus b cos nt. And now we will solving the equation x is equals to e power of beta by 2 d of sin of nt plus pi. If beta is small quantity, then amplitude, that is e power of minus beta t by 2 d is gradually decreases with the time and tends to 0 at t approaches to infinity. Now critical damping cases, that is beta square by 4 minus omega square is equal to 0. That is case 2, and the system does not oscillate and damping is just adequate such that the system returns to its equilibrium position in the shortest position possible time. Now example is like this. This is the hand pistol, and this is the door closer. Now automatic door closer. So the recoil mechanism in most guns are also critically damped, so that they return to their original position after the recoil due to finger or firing in the least possible time. Now in that case we have limit n tends to infinity a plus beta t by e power of omega t is equals to limit n tends to infinity beta by omega e power of minus omega t is equals to 0. Now the last case is over damping cases, that is heavy damping, that is beta square by 4 minus omega square greater than 0. The damping is so great that the displaced object never oscillates above, returns to its equilibrium position very slowly. That is denoted with the over damping cases. So example for this, this boy is sleeping in this position. The coiled spring matrices where the spring slowly returns to a equilibrium position when a person lies on the matrices. So this is the example for the over damping cases. Now for over damping, we know that beta square by 4 minus omega square greater than 0. Therefore we get as x is equal to c e power of minus beta by 2 plus lambda into t plus d e power of minus beta by 2 minus lambda of t. So in this case the motion is non-periodic and non-oscillatory, so it is called as the dead beat. So both the exponentials decay with time, so therefore it tends to 0 at t tends to infinity. Now the graphical representation shows the strong damping, critical damping and under damping, critical damping and over damping is there. So this is the indicate the damping cases. Now the application of damped oscillations are there. So that is an application of a damped oscillation is the shock absorbers of the car, which provides a damping force to prevent the excessive oscillations. If the shock absorbers are badly worn, the car becomes too bounce, and this is unfortunate. Now another application of the damped oscillation is the shock absorbers of the human body. Scarce body moves over the bumpy snow smoothly while his her tights and claves act like a damping spring. Now the spring door is also example for the damped harmonic oscillations. Is this like this? Damped force oscillation, in order to overcome the damping effect of the medium, an applied force called as the driving force is generally applied. In such a case the system is called as the damped force oscillator. Now we get the damped force oscillator equation is there, that is d square plus beta d plus omega square of x is equal to 0. Complementary function of decays with time. For this reason this part of solution is called as the transition solutions. So thank you everyone. My class is over in 34 minutes because of the topics are very less. Thank you very much.